Good morning. Let's continue our discussion of statistics, and let's start to get into maybe the branch of this class, from some of the final things we do in this class even, that maybe is most instantly applicable to the real world. You're going to find that in this Module 9, as we talk about scatter diagrams, correlation, and regression, that I'm going to have to disappear behind the screens of an Excel file maybe to make some of this seem a little more active and real. Our calculator will continue to be quite useful for this, but I really want to give you a flavor of how this happens in real life. In real life, we use very powerful programs. I've mentioned these before. You have SAS, SAS, and SPSS, and R maybe are some of the big common ones. Mathematica and Maple maybe if you're more from the mathematics side than statistics. All of these are very powerful computer programs and extraordinarily expensive, particularly if you're trying to do this in a for-profit model, with maybe the exception of the R, programming language and calculational suite. It's what I use myself. We'll also use Excel in this class for us, mostly because Excel is a very visual presentation. It tries to make this stuff happen very nice and cleanly, and so you can see every piece of your process. So I'll talk for a little bit maybe in this video and try to describe everything in this section on linear statistics, perhaps. Well, not everything in linear statistics, but everything in our section at least. And then I'll have a couple extra videos in this for this module that discuss about the Excel specifics. And then I'll go behind the scenes. But the basic idea is this. Oftentimes, we have paired data and we have sets of samples. And we saw that in the last section with hypothesis testing. And there were two cases. Sometimes our data was paired and we were able to say yes at a particular level for a particular patient. We had before and after, and so we had that perfect pairing, and that's nice. But in the case of the before and after scenario, we kind of were measuring the same stuff before and after. And then, of course, we had two-sample hypothesis testing where there was maybe independent data, but still we would like to compare the two categories by columns. What you see over here is an example of something where we can go even a little bit more than just saying before and after. We're trying to understand a relationship. And if you think back to some algebra class maybe that you took, relationships, we tend to describe those in mathematics and statistics with a function. So here in the first column, I have hours per week. It describes how many hours per week some of my students have engaged in their online homework product only. This is by no means all the studying the students do, but it is how much time they spent interacting with homework. On the second column, we have their score in the class after they had completed that much, well, maybe not say that much homework, but their current score in the course. Okay? So someone who spends 1 hour per week working on their online homework product only has a score of 54%, whereas someone who's spending 5.7 hours per week in their homework product is almost within an inch of having a B in the course. And so you kind of would expect the more time you spend studying, the higher your grade would be per week. And again, I hasten to stress, this is not all the students studying that they do. This was only a poll, so you could if you asked these students how much time do you spend studying, they'd give much larger numbers. And that would be legitimate because you spend time reading the book, you spend time working through examples not online. You print out your online homework and just work on it and just try to type in the answers at the end rather than working through the process. But maybe this is some measure of student effort on one side, and we see some level of reward for that effort on this other side. And any time you get into the scenario of cause and effect, we start to want to try to measure that in statistics. Now, I've just said a word that made anyone who does stats a lot flinch. I said cause and effect. And so I'm going to have to be very careful to get myself out of a verbal pickle a little bit later. But first of all, let's look at this. Maybe you're used to an x and y axis, x-axis and y-axis, and we've got positives and negative numbers and whatnot. Oftentimes in statistics, we're focused on positive measures, particularly if I'm talking about something like time. So you tend to see that we get these plots where we've just got x-axis and y-axis, and we've got this force positive. You see this a lot in business too. But you can pretend like my y-axis stretches down and my x-axis stretches left, if it made sense. First of all, let's talk about some language. Oftentimes we call x-axis independent variable. It's a variable because it changes. It's independent because this is the part that's under our control. It's free. It can do whatever it wants. You could spend 1 hour a week in your homework suite, or you could spend 50. It's kind of all up to you in a certain way. Another word for this is sometimes called, and different textbooks use different phrasings for that. I think sometimes this one's also called the explanatory. I'm trying to look at the spelling of the word explanatory to make sure that I don't mess it up, but I think I managed to make it right. This is sometimes also called the explanatory variable. It's the one that explains what happens. Again, it's the independent part, it's the part under our control, it's the thing that's free to kind of do its own thing. But then we have the y-axis, and this is the part that we then would call the dependent variable, also sometimes called the response. It still varies, it does different things, it's not constant or fixed. However, it is locked down a little bit. We have this sense, possibly, that depending on how hours of week go, so too does the score. There might be some sort of link between those. Before we talk about this specific example, let's just try to draw some imaginary examples, and for that we use this thing in statistics that we call a scatter plot. Instead of looking at just a couple of points, we tend to look at dozens of points, and so we throw a bunch of points on a grid, and this looks like a whole bunch of scattered dots, so we call it a scatter plot. And let's talk about maybe the different scenarios we could have. So for a moment, let's keep this example in our mind that this is what we're trying to do, but let's develop the logic, the philosophy behind this. Suppose that I have on my x-axis hours per week, and suppose I have on my y-axis score. There you go. I said I'm leaving that behind because I'm not going to plot out specific numbers right now. Let's just try to imagine the different ways this could go. Now, in a perfect world, maybe these guys would be very much connected, right? The number of hours a week you spend doing your homework is directly related to how well you do on that homework. So if we increase, maybe here's 1 hour and here's 10. Maybe here's a score of 10%, and up here's a score of 100%. So possibly, if we spend very little time on our homework, we get a very low score. And then some people spend a little more time, but they didn't get much better. But finally you reach some kind of breaking point of time. You've spent enough time to start doing things. And so what you see here is I'm drawing a scatter plot. And each one of these dots has a particular time value attached to it, as well as a particular score between 0 and 100%, right? And notice how I've drawn this. It looks overall that as I increase the time, roughly, I'm increasing the score as well. It's not always the case. Look, here we've got a little band of people who are spending about the same time, and some of them seem to score very low, and other people in this band seem to score rather high. Still, here we seem to have some sort of cutoff, right? Everyone who spends less time than this has a very low score, and everyone who spends more time than this starts to have some kind of respectable score accumulated. It's not just, 2%, 5%. So at a certain point in time, something happens. And maybe we could cut that even further, right? And say, everyone who spends more than this is inside of passing territory for the most part. This is an example of something that overall is giving us this, as one increases, the other increases. The relationship between these two, which in statistics we call correlation, we would say this overall is positive. As hours increase, score increases. Right? So we would call this a positive correlation. And you'll see that as you look through this section of your textbook. Let me draw some different scatter plots. Let's keep our axes the same here, but let's just focus on maybe looking at some different dots. The last thing I drew was pretty narrow and tight, right? It kind of increased along this pattern. What if I had this? I need to make them not so like lines and more like dots, okay? Well, one, there's a lot more students here than the last time, but let's take a look at this. Certainly, again, overall, kind of look that the lowest that I've got here is lower than the lowest we've got here, so it's still kind of going up. Here, the highest point we've got for this side of the graph is lower than the high points we've got over here. So definitely, as you move from left to right, we have this sense of increase. We would probably still call this a positive correlation overall, but it's a lot rougher, right? We don't want to assign, this isn't as good of a fit as when we only had something that looked more like a line. This should be a better correlation fit. So this correlation number that we discuss should be able to somehow talk to us about fit, and maybe it should go between 0 and 1. The closer it is to 1, the better we should have a perfect positive correlation. What makes this one not perfect? Well, for any particular x value here, notice we could have this y value, or this y value. So we've got some options here. So this isn't a perfect straight line fit, right? We've got too many options at any particular category. However, what if we had the opposite scenario going on? Sometimes I have students talk to me and they tell me, I don't want to tell you how long this homework took. What does that mean? Usually it means it took a long time. Or you'll hear people say, oh, I just don't understand it. I spent 15 hours doing that assignment. It was a horrible essay. What does that mean? It kind of means that sometimes we have the opposite sense, right? Sometimes the idea is that if it takes a very long time to do something, you must not be very good at it. Well, if that's what you believe, again, we're ignoring this actual data over here. We're just kind of figuring out all the different ways this could work. If you have to be very quick to be good at something, think of it this way. The first person who walks out of the final exam, the fastest person, do you think that person is scoring the highest in the class or the lowest? Sometimes I think folks have the idea that the faster you are, the better you're going to be doing at things, in which case we might imagine that our scatter plot looks something like this. You have to spend 10 hours a week on your homework, just the online homework part. You don't really understand statistics all that well, maybe. This is a pretty narrow band, right? It looks like a good fit to a straight line almost, but now it's going in the other direction. Now as hours go up, the score is decreasing. We have a word for this too. We call this a negative correlation. And this is a pretty good negative correlation. Let's talk about some other things that are negatively correlated. Let's go away from this practice example for a second. Let's talk about tax dollars paid. And let's put this up here, not as score anymore, but my happiness. The more tax dollars I pay. So now this is not thousands of dollars or something, right? the more I pay in taxes, the lower my happy is. And that's going to be probably true for you too. Nobody likes writing out a big tax check at the end of the year. Negative correlation. So in that case, it seems like we should do a little bit more, right? We would like to increase this idea of correlation and not just start it at 0, but we'd like to also somehow code in this idea of negative, where maybe the idea of -1 would be something that's a perfect set of lines that I could just draw a single solid line here through that hit them all. But if I don't have that quite perfect possibility, something a little bit messier than a perfect straight line should still be somehow a negative correlation, with the idea that at some point we reach 0 and have no correlation at all, and then maybe we start having a positive correlation. And in fact, that's the case. The correlation number, which in your calculator and on Excel and pretty much everywhere else is labeled with lowercase r. This is the correlation coefficient number. It's very, very messy to calculate by hand, so we tend to let technology do that for us. In fact, I don't even think I'll show you the formula, though you can look it up in your book, and it is messy. And this correlation coefficient lives between -1 and 1. And the closer it is to -1, the more it looks like a direct, nice, straightforward negative line. And the closer it is to +1, the more it looks like you've got an increasing positive slope line. And things that score 0? Well, things that score 0 are just things that are pretty much random. No real line, just a bunch of messy dots. So, what we're looking for specifically in this section of statistics is sets of data that we suspect that it makes sense that some of this data maybe explains some other parts of it. And it makes sense, at least in my mind, that the hours of week that a student might spend on their homework should perhaps predict their score. So you look for things that are related when you've got columns of paired data, and you think about things that maybe would help predict those. The explanatory variable, the response variable. The very independent part and the part that's then dependent. And we would expect that anything that we do in this section will become better in terms of how much we can do statistics on it, the closer this correlation is to the number 1. So, the first thing that I do when I've got this kind of paired data is pop it maybe into my calculator or into Excel. So I've already entered these numbers into my data columns, but just as a reminder, go ahead and turn your calculator on. Let me get out of there. Turn your calculator on, go ahead and hit that data button, and I entered in all of my hours per week in list 1 and all of my scores there in list 2. And then you hit second and you hit statistics regression, and now for the first time we go down to 2 variable statistics, hit enter. We tell it that our X data is in list 1 because that's where I put it. I tell you that my Y data is in list 2 because again that's where we put it. Our frequency again is 1 because we're not doing mixed frequencies here, and then we hit calculate, and then I'll go ahead and type this enter button. And when I do that, our calculator gives us lots of information. It tells us that we had 16 pairs of points in this list of hours per week and scores. And it tells us the average hours per week, that's the X bar, 3.3¼ hours was the average number of hours per week that students spent in that sample. Scroll down a little further and you'll see Y bar. This is the average score that was gotten for that up and down Y measurement. In this case you see the average score is a 73%. This class was doing pretty well. Notice that it calculates the sample or the population deviation for both the X direction and the Y direction. And if you scroll down far enough, it gives you all sorts of pieces. If you look at your formulas, these calculated pieces might be helpful to help you calculate some things. But if we scroll down far enough, you see right here is R. And R is my correlation coefficient. And R is this number right here. that we want to calculate. Again, if you look inside your textbook, you'll find a formula for that. And you'll find that that's just a little bit messy. So let's talk a little bit deeper about what kind of numbers I want to get out of this. So let's erase some of this stuff and talk about what this can look like. And then we'll get to our specific example. I'll just erase all of this, I guess, and redraw my x and y axis. Okay. So I said that a positive correlation would be the part of that correlation formula between 0 and 1, and the closer you are to 1, the more you think that you've got some sort of decent positive correlation happening. And contrary-wise, the closer you are to -1, the more you'd expect a negative correlation to happen. And when we have in fact looked at our formula sheet here, not our formula sheet, but our calculator rather, we had seen that the correlation for our calculated value of 0.4356 is suggesting to me that we do in fact have some sort of positive correlation here. Remember, on the number line, 0.43 is kind of about halfway-ish in between 0 and 1. So it's not a perfect fit, but it's getting on its way to maybe having some sort of positive correlation going on there. So as we look at these fits, here's our goal. Let's look at a very few sets of dots. Again, I'm not plotting these numbers yet. We're not quite there yet. If our correlation coefficient is close enough to either a positive straight line fit or a negative straight line fit, so if it's kind of locked away from 0, so maybe let's look at this, right? Our correlation number goes from -1 to 1, and here's 0 in the middle. So maybe we don't like things that are close to 0. So the stuff in here, maybe we kind of want to X those out, right? But when our correlation numbers are fitting on the outside here, or fitting on the outside here, that's when we start to think that we have some sort of decent line shape out of our scatter plot. And again, if I just look at a few points, these few points, they would probably have a correlation with something like, I don't know, 0.7, 0.8. Very few dots, and it's clearly, you can almost see the line. In fact, let's draw a line that would fit these. This line we're about to draw is called a regression line. And notice, I could draw a couple of lines, right? What if, and I don't know that I have a very large object here. I normally have a very big straight edge in my office, but let's see what I can find. We can use a calendar, I think. Notice all the different ways I could connect the dots. What if I just connected these two dots together? Follow that line there on the top. I think that's clear enough on the video what's happening. If I just connect these two dots, notice that these three dots above it are kind of, well, over my line. I haven't really made a very good prediction line, have I? If I connected these three, well, I've got 3 of the 5 overall dots, if I don't erase these two down here. So let's see if I can do this way. If I connected these 3, it looks like I could almost draw my grid on top of them, but still, those bottom 2 I've kind of undershot quite a bit, right? So what if I kind of draw something halfway in between all of them? Something that tries to average out those distances. If I did that, we would call that a least squares line. Let me draw a least squares line for us. Pretend that's a straight line. This is what we call a least squares regression line. Least squared line. We normally call this line y hat. Notice that it may touch one of our raw data points, Or it may kind of try to find the narrowest distance between all of them, because we saw that if we bump this line and increase it a little bit so it goes through all these top ones, it's really far away from the bottom ones. And if we instead draw it so it passes through the bottom ones, it's really far away from the top one. The goal is to create the smallest distance between all the points. That's why we call it least squares. We use square to do the distance, right? Just like we did back when we were calculating standard deviation way, way back at the start of the course. So this least square line is called y hat. Our textbook writes this out as a plus bx. Our calculator is going to calculate this line for us. Maybe you remember in algebra class where you had mx plus b. The number in front of your x is your slope, and b is that y-intercept. In statistics, we tend to use some different letters. We tend to use a plus bx, but watch out, some calculators use ax plus b, and I'll show you exactly where you can look on your calculator, or any calculator in fact, to find out which version your calculator is using, so you know what numbers, because of course you need to make sure you use the right a and the right b for everything. This least squares line here is a very interesting line. It tries to fit some sort of minimal distance to the whole messy business. It tries to give us the best calculation it can, so that we have a line that's, for the most part, perfectly set up. Because again, if I made this line any taller, then it would start to get really far away from the bottom ones. If I made it any shorter, it would start to get really far away from the top ones. And so this least squares fit line is the best possible line that fits all these points. When you fit a line like this, you want to watch out for some possible mistakes. So let's take a look at what those mistakes can look like. Let me redraw this dot here so there's enough space so that you can see what I'm talking about. All right. All the black dots on this board, including this one, are what we call raw data. So we write them as a coordinate pair, x for our explanatory variable, y for our output response variable. And if you follow this dot down to our least squares regression line, let's talk about this coordinate point. Definitely it's the same distance left and right as the one right above it, right? I've drawn it right down in a straight line. So the x value is still x. But the y value is not quite as high as the actual dot was. The y value is the y value from our least squares line. We call this y value y hat, with that little caret symbol on top. The difference between these two, we want to focus on that height difference. Well, what is it? It's y minus y hat. And this difference right here is the difference between what the least squares line predicted the response variable height was for y and what it actually was. So if x-axis was going to be, let's say, units sold, units produced, let's say, and the y-axis was going to be cost, and we had these dots on the least squares line, this y hat output is telling me that when I produced this many units, whatever this value is, I don't know, here's 1,000 units, here's 10,000 units that our factory is producing. We have some factory that's producing stuff. I would have predicted a cost of this much, and in real life I would have been hit with a bill that was just a little bit higher. This difference is called the unexplained error that we've got. Sometimes the unexplained deviation. Unexplained deviation. It's y minus y hat. It's the distance between our line and one of our actual real-life points. It's the part of the real-world scenario that our blue least squares line doesn't explain. So we call this unexplained. However, if if you look at this, you'll say, well, that's quite a bit of unexplained error. I don't like having more costs than expected. That sounds bad. And here, what have we got? We would have a prediction up here, but in fact we would have had less costs. So we would have taken money that we could have used to pay bonuses to keep our workers happy, and we would have reserved it to try to pay off some bills maybe. So you look at these and you say, well, that looks pretty bad. What's the thing that we should compare to decide, is it even sensible to talk about this blue line? What you compare it to is y bar. Y bar is your average of all y values. Right? And in fact, we had calculated y bar already. Let's take a look. For our data, remember back when we had the data and we'd put it into the lists there in the data pieces, when you'd hit second and gone to two variable statistics and asked it to calculate that, it had already calculated y bar, which is a flat line at a particular point. I've drawn that out here as a dashed line. Notice that if we just did the average cost, if we had just focused in this factory example on all the costs in general and just calculated the average, did a point estimate rather than use this blue regression line, then we would have had to use y bar. And notice here, on this thing, we've got another point. Again, the x value hasn't changed because we're just focusing on y's, but our y height is now y bar, so we once again have a distance between here. And this distance, y hat minus y bar, is what we call our explained deviation. So here's what we're faced with. Sometimes we're given lists of numbers. And then when we have more than one list of numbers, we've got a choice to make. We have to decide, does it make sense to put these two lists together and talk about them in relationship with each other? If our correlation coefficient is far enough away from zero, either in the positive direction or in the negative, we start to think that we probably have something that's roughly a straight line. If we think that we have a straight line, we're going to use technology to power through the formula calculations to give us the exact formula for what we call our least square line. We know that our least square line is doing good work because overall, we're going to have a certain amount of deviation between our real-world results, which I've done with this black dot, versus the average results that I would have expected, which is this red dot on the y-bar line. What I'm trying to say is that if we didn't have this module, the best we could do for our outputs here would be to say, look, I can talk to you about a point estimate, y-bar. Sure, we could slap a confidence interval around y-bar, but y-bar would be our best predicted guess as a single point estimate. If our correlation is high enough, either in the positive direction or the negative direction, then we start to think that maybe I can shrink this overall distance just a little bit. I can explain some of the difference between the real world and my point estimate prediction by recalculating a different relationship, not with a single point, but instead with a line. We push ourselves forward to a new level of accuracy by making an assumption that maybe we've got a couple of sets of related information. Maybe the x values in the first column can allow us to explain what's going on, and the y values are some sort of response. So now, let's look specifically at our example with scores, with that sort of idea. Let's take a look. So one more piece bad drawing. In fact, in a second, this video will end and you're going to go and look on another video that's exactly the Excel file where I'm going to calculate this out, and I'll talk over that, of course, and explain to you what I'm doing. You'll see how to calculate that. We'll have a very beautiful chart and everything will be great. But if on the x-axis I put hours per week, And those hours per week seem to range from 1 to 6. 1, 2, 3, 4, 5, 6. 6 hours, 1, 2, 3, 4, and 5. And I seem to have scores on the y-axis. And those scores seem to have a low of 0.54 and a high of 0.88 somewhere here, I see. So let's go ahead and draw this not to scale. Use that jagged squiggle thing there. Do a very good job of making that jagged. There we go, something like that. I think was back when we were talking about good data drawing business. I've labeled my axes, but here I'm going to have 0.5, 0.6, 0.7, 0.8, 0.9. Of course, up here at the top we'll have 1.0. Well then, at the one column we've got this 0.54, so here's my scatter plot. At 2 we've got 0.54. At 2.2 we've got 0.88. At 2.3, 2.3 is about here, we've got 0.72. I'm doing a very bad job of drawing this, and this is why you let technology do this, but this will help us see roughly what's going on. Almost 2.5. We've got exactly 2.5, we've got 0.75. So we've got this one, and a little bit before that we're a little higher, so we've got that point there. At 2.7 we're almost at 3, we've got the 0.74. And again, you're seeing why we want to do technology to do this. 0.75 again. 3.1s we're in this ranging from 61 to 77. Notice that for the same input of 3.1 hours, you could be a 61 or you could be a 77, so we've got some differences there. Alright, 3.2 is 76. This is why I don't draw things by hand, because it's looking very, very bad. But anyway, 75, plus my ADD is kicking in here, I'm getting very bored. Suddenly we jump to 4.9, and that's almost here. 5.0, we're at 6%, that's a little higher. 5.2, 76. And 5.7, almost 6 hours, we've got 79. You'll see a much better picture on Excel in a second, I promise. But looking at this, you can see that, yeah, overall it does kind of look like it's going up from left to right. So now we can go ahead and take a look at the correlation. And again, remember when we did that, inside data we had entered our list of column numbers. Then you go to second in data again, and this gets you into statistical regression. Now we're going to scroll down one more line to the equation lin regression, for linear regression. I warned you that our formula in general is a plus bx, but I said that some calculators use ax plus b, and in fact ours does that. Notice we have ax plus b. So I know the number the calculator labels as a is going to be the slope in front of my x, and I know the number our calculator labels as b is going to in fact be our intercept. Sorry. So I'm going to go ahead and hit enter. Tell it that my x input values are in list 1, my y output values are in list 2, the frequency's 1, just go ahead and agree to that no and ask it to calculate. And when I do that, scroll down for a moment and take a look here at this R number, which was 0.4356. Let's round that to 0.44. .44 is living in between 0 and 1. It's almost halfway in between that line there. We start to think that maybe this looks something like a straight line. It's not 0, it's 0.44. That's a little bit away from 0. And as you look at the scatter plot, you see, yes, this looks somewhat like a straight line. Here's what we do. If you look a little further in your data column, we can look at some other numbers too. Our data's still here, so if you hit second and you just go to two variable statistics and tell it that you've got things in list 1 and list 2, we'll notice that you can find x bar, which is the average number of hours, 3.25. Let's go ahead and draw that. 3.25 is here, so here is my x bar. And if you scroll down just a bit further, you'll find your y bar of 0.73. So here's 7, here's 8, here's 7.5, so let's say here is 0.73. So notice, here, if we were to make a least squares regression line and try to overall fit something between these dots, I would expect to have a line that looks something like going through here. And if I did that, certainly in this right quadrant, my line would be doing something like this. And notice that in general, I would be getting some more accuracy for some of my points than if I just used the point estimate of 0.73. We would be able to get, we'd still have some unexplained error, but we'd be able to explain some of the error between this flat line and where this point is. Hopefully we could recalculate that. That would give us slightly more accurate estimates for what I expect a student to do if they work 5 hours a week or 4. So let's take a look at what our line equation would be. Again, if you look in your book, you will find the pieces of that formula, and in fact, we're still on the same screen here where we had the y bar. If you scroll down far enough, you'll find that your calculator gives you many of the pieces. It sums all the x's, it squares each of the x's and sums them, sums all the y's, squares each of the x's and sums them, multiplies x's and y's together, but finally, we get ourselves some a and b values. And when we look at those a and b values there in our calculator, or if you go ahead, maybe I should show you this again too, if you go ahead and hit statistics and go down specifically to the linear regression line and hit enter, your calculator again reminds you right here that it's ax plus b rather than your book formula of a plus bx. So it's just telling you which goes where. This a number goes in front of the x, this b number is my intercept. So let's go ahead and draw this equation here. The equation I'm trying to draw has an intercept at 0.626, so let's call that 0.63. And if we go out a distance of 1, we're going to be at 6.3, 6.7, 6.78, almost 8.3 here. I'm not very good at drawing them. This is totally not drawn to scale. If we draw this out, then it will look something like this. And this line is our y-hat line. We call it our least squares regression line, the linear regression line, and its formula is going to be that a value, which I will round to 0.03, plus 0.63. Again, I'm getting those values right from here. This is the number in front of your x, this a, so 0.03, and then this is your number b. I'm rounding 0.626 something to 0.63, and that's your intercept there. When we get this, notice that overall, this line gives us some beneficial things. Over here at the low values, it's telling us don't use point estimators up here at y bar, instead use lower ones on my line. It tells us you want to lower your expectation for a grade when you're to the left of 3.25. And when you're to the right of 3¼ hours per week, it's telling you don't use this as an estimator, bump your estimate of your grade, expected grade up a little bit. With a score like this, we get ourselves a formula. Y bar equals 0.03x plus 0.63. This formula, we can plug any value we want in for x, so maybe I can put a blank bar here, and this will tell us what score we expect. This will make sense in between our range of 1 hour all the way up to that 5.7 hours that we initially had in our list here. You shouldn't necessarily use this to project off into the future. What if I spend 20 hours a week? Well, that won't work. This formula is not designed to cope with something like 20 hours a week. So let's say you decide that you want to spend exactly 4 hours studying. Well, you want to calculate 0.03 times 4. plus 0.63. Grab my calculator to help me do that. 0.03 times 4 gives me 0.12, plus 0.63 gives me 0.75. If I spent 4 hours in this program, I would maybe be expecting in this class a 0.75, roughly, as my score for that homework assignment. So what this whole process does of scatter diagrams, correlation, and regression gives us a way to talk about what if we think there should be some connection between hours per week and score. Some things to watch out for. Correlation is not causation. This is rule number 1 in statistics. That's because we were clever and put it this way, and that makes sense to us in the world. But as far as the calculation is concerned, it would have given us same correlation, a same positive correlation, if we had reversed these columns around. This 0.44 number that we got doesn't particularly care what order you put these in, which means then you'd be saying the kind of weird statement, people with high scores are forced to study longer. That sounds a little odd, maybe. Famous things, and I talked about them very, very much at the beginning of this class, confounding variables. There was a very large city, it was famously did some education research, and it found out that the more trees there were on a K through 12 campus, the better those students did. There was a strong correlation. As I recall, the correlation was over 0.7. So it was very, very strong. It was very significant. However, when it comes right down to it, of course, trees on a K through 12 campus, more trees don't actually have anything to do with student success. They have everything to do with how wealthy the parents were. And of course, wealthy parents are able to afford things like tutors for their children or hire competent teachers. So you'll find that just because you've got a correlation that suggests that we've got a linear fit line possible, doesn't mean that it always makes sense. And also you'll find that you have to look carefully. You'll see this a little better in the Excel plot, but you're going to want to look carefully at the line. Sure, the correlation number is nice, but you always want to sort of eyeball that scatter plot and say, does it make sense that I put myself a straight line here? Is that reasonable to do for this particular problem? The last thing I want to talk about before I turn you over to myself on Excel is the fact that we can take this correlation number, R, and we can talk about R squared, which is just R times R. And if you take a look at your calculator inside that linear regression area, so one last time, second data, scroll all the way down to linear regression, enter, 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 I don't know how many enters, but at least 4. And notice that it has R squared here, and that R squared is 0.1897, so we can round that maybe to 0.19 in this case. Put wiggly equals here. This R squared is called the correlation coefficient. And I don't know where I've got room to put this. I should say something about correlation coefficient. Coefficient of determination. Sorry, I just realized I misspoke. R is the correlation coefficient. R squared is the coefficient of determination. And there's a couple things that you want to know. Let me put these in the same order that your book is talking about. I would say that, I guess, looking at this, I guess the simplest thing to say about this, in keeping with this textbook, and it means the same stuff here, I'm just looking at your box, is that R squared talks to you about how much explained variance we have over everything else. So remember, this, we looked at here, this distance up here would be unexplained. This distance here would be explained. So for this dot, our linear line did us a favor, right? It said, no, don't use 0.73 as an estimator. Use this point up here, and that point was pretty close to accurate. However, here our line did not do us favors, yes? This part here is unexplained. And this part here is what we were trying to explain, and it kind of overestimated what we were doing, overshot what was trying to happen. So this made this part a little bit messy. If you take the total amount of variation, and again, when you calculated the two variable statistics, you can see the variation for each of these categories individually. If you look at the total amount of variation, and then you try to create a ratio that describes how much of that overall variation is explained by our line, that will give you a number that we call the coefficient of determination. And remember, coefficient of determination squares, so 1 squared is just 1, so coefficient of determination lives between 0 and 1. And what that tells you is what percent of all of the turbulence in our y-value response data is being explained by our blue line. So when I get an r squared of 0.19, I can tell you that 19% of the overall turbulence between these categories and this relationship here is explained away by my blue line. So that's better than nothing, right? If I had nothing, I would have 100% of the variance that I had no real explanation for. So what this tells you is this blue line is better than just using point estimators. It's giving me something to go on. And you'll find in different disciplines, in different arenas of scientific study, and I know this is going on long, but this is the only talk video I think I have for this section. The rest is Excel, so it's okay. Bear with me. Different r-squareds are considered good in different areas. So in some very, very strict formal place, maybe I would like r-squareds that were very close to 1, because they would explain most of the variance. On the other hand, in areas like medicine, if I have an r-squared of maybe 0.03 or 0.05, which only explains 5% of all the variance, and there's 95% of the variance that I don't have a clue on, still, that extra 5% is very important in medicine, and it's very useful. So that's one thing to think about. Where does a good r-squared number come from? So the question that you want to ask now is, how could I get that r-squared higher? The higher r-squared gets, maybe the better my model has become. And right now this model isn't really all that great, right? Because look at the beginning. The correlation was only 0.44. It was only about halfway between none and yes. So it was kind of, if we want to attach a verbal word to that. Well, let's go back and look at our data. Can we imagine some scenarios that would say these guys aren't going to be a perfect fit? And the answer, of course, is yes. Let's take a look. Notice that here's two students who spent exactly the same amount of time, 3.1 hours per week. 3 hours and a few minutes. One student scores a D, and the other student scores a high C. That's a lot of difference between these two students. If I wanted to get a better model to predict grades, I would have to ask myself, and maybe it's the easiest to see it here, why are these two students different? From my explanatory variables, the stuff that I was trying to use to explain it, we weren't able to lock things down all that well. Because of this big difference here, that's exactly what leads to this correlation not being all that good. The answer is you want to come up with more predictor variables, more explanatory variables. What I want to do is I want to crunch down this hours per week and say hours per week and squeeze myself in another column. And that column could have all sorts of data inside of it. But let's say I happen to tell you that this student happened to have waited 3 years since their last math class. And that's so messy, I know you can't read it. So this student has had 3 years since they've last touched math. They have done 3 years with no math whatsoever. Whereas I tell you, this student just got out of calculus yesterday, last term. Now, these aren't number variables, but if I wrote that explanation right there in that column, you would instantly say, of course, someone who's done 3 years without doing any math is going to have a rougher time of picking up statistics than someone who just got out of a even more complicated math, maybe calculus. So of course we would expect a difference between these students. If I could somehow code this into numbers, maybe those numbers could help me generate more predictions. The problem is, of course, if you add more predictive columns, you stop leaving the area of linear regression, and you start moving into, it's still kind of linear, but we tend to look at it more as a plane, perhaps. You start moving into what we call multiple regression. I think your textbooks sometimes use bivariate versus multivariate. Bi meaning two, just an x and a y, and multi meaning x's, y's, or excuse me, x1, x2, x3, and then a single y output. That's your response value. Luckily, Excel will let you do multiple regression. And it overall behaves exactly the same way as this bi-regression. It's just a little harder to draw on a board. So again, we're going to move ourselves into Excel to take a look at that. If I had more explanations for how the students behaved, what I would expect if they were good explanations is that I would find my correlation overall starts to get better, and I would expect in particular that this r squared value starts to get higher. As I add in more predictors, I should be able to explain more and more of the overall variation. So with a single predictor, I can only explain 19% of the variation. Better than just using y bar, but still, 18% is not all that much. So maybe I start to ask myself, how many years has it been since the students last done math? As the years since the students last done math increase, maybe I expect their score to decrease. Because it's been a long time, math is a language. I've said that before. We talked about, I think, Russian in math weeks ago now. So if you're looking to explain something using a regression line, you want to strongly consider multiple regression. And I think now is a perfect time to stop the philosophy side of this and switch us over into Excel, because we can take a peek at how this looks and we can see some very pretty charts that maybe will try to explain some things. So until I see you in just a few seconds, be safe and maybe give yourself a drink of water and open up Excel on your computer.